Okay, so on Monday we had started with the grand canonical partition function, and we first converted we were basically looking at systems which exchange also the number of particles with their environment. So just like in the canonical, in our discussion of the canonical ensemble, we first started by extending our system so that it becomes an isolated system which doesn't exchange any energy or number of particles with environment. So we could use the ideas of the microcanonical ensemble. We looked at the entropy, and then from that discussion, we asked ourselves what should be the energy of our original system. So that we had the entropy is maximum, and we had seen that both the chemical potentials and the temperatures had to be equal. And then we said, okay, what about the probabilities that our original system would have a given number of particles, and in a given microstate for those number of particles? Well, these derivations are more or less follows the same reasoning as we had done in the canonical ensemble. Again, we found this exponential dependence of the probability, and the normalization factor we call the capital Q, the curly Q, is the grand canonical partition function. And we had also, well, later on we will see that the important thing is the logarithm of this grand canonical partition, which we call the Q potential. And we also derive the same result using what's called the ensemble theory. We had many copies of our system, each having a different number of particles in a different microstate. And then we ask what is the most probable distribution of these numbers NRS, where NRS is the number of copies in our ensemble, which has NR particles, and in the microstate S. And we had seen that whether we looked at the most probable distribution, we basically obtained exactly the same result as our previous discussion using the results of our microcanonical ensemble. We didn't discuss it, but if you would calculate the average value, expectation value of these numbers NRS, you would still get the same number.
Hocam, burada expectation n olması gerekmiyor mu? U'nun altındaki.
Where? This one.
Yok. N eşittir dediğimiz expectation n değil mi?
Well, okay, the notation I will be using exchangeably. I will have the average, and I will sometimes show it with bar. Sometimes I will also drop the bar. So depending on which ensemble we are considering, you should always, if we are talking about the grand canonical ensemble, n will always denote the average number. In the canonical or the microcanonical, n will be the exact number. But as we will see today, in most cases, the fluctuation around this expectation value is negligible. So we can say that even if the n is changeable, with 100% probability, it will have whatever average value it has. With the probability of any significant fluctuation going to 0. And then we asked ourselves, okay, we defined this Q potential, and we had seen that just taking its derivative with respect to alpha or beta, we could calculate various averages, but what does Q stand for, this Q potential? And to determine that, we looked at how Q changes as we change the parameters in our problem, like alpha, beta, or V. You see, your friend was asking, why don't we have in this expansion dq, why don't we have any term which contains D and R? But you see, the parameters I'm controlling are alpha and beta, which will be the chemical potential and the temperature, and also the volume. As I change volume, the energy of the microstates will change. So ES will change as I change my parameters. But nothing will change NR for a given state. No parameter. If my system has NR particles, nothing will change. And then we had seen that this Q potential is actually nothing but PV over KT. So if we calculate Q potential, we are actually calculating this ratio. And, well, remember this expression. Probably in the second hour we will be using this expression. This gives free energy. It's just n times mu. its differential is minus SDT plus VDP and plus mu dN. And, well, then we looked at several examples. Yeah, in all these examples, we basically started by saying that, okay, let's calculate the canonical partition function, Qn somehow. And then once we know Qn, we can just sum over all n's, multiplying it with the nth power of fugacity, and obtain the grand canonical partition function. So in these examples, at least that was how we proceeded. Then you can ask, okay, so what's the point in using the grand canonical partition function if we first have to calculate the canonical partition function? But we will see next week that in certain cases it will be easier to calculate the grand canonical partition function at first. We can directly calculate it. And, well, basically that was, we looked at, okay, the free particle and localized particles. And then, in fact, these kind, if you like, toy models allows us to also study what we call the phase transitions. You see, if we look at solid and vapor phases, then we had various results. For example, when we have such a equilibrium between these two phases, and we have both of those phases, the pressure depends only on the temperature. It doesn't depend on the volume. Of course, this is true if we have an equilibrium. If you keep compressing the gas, eventually all the gas becomes solid, and then, of course, pressure depends on the volume. If you expand the volume further, eventually all the solid will evaporate, everything will be gas, and then it will satisfy the ideal gas law. But as long as there's an equilibrium between these two phases, the pressure only depends on the temperature. So what happens when you compress the gas in this equilibrium system is that you would expect, since the V is decreasing, pressure to increase, but what happens is the number of gas molecules decrease. Basically, they solidify if you compress them. Similarly, if you expand the system, what happens is more solid particles evaporate. So the number of gas particles changes. So that pressure depends only on the temperature and not on the volume. And of course, we also had seen certain cases, critical temperature when these phase transitions appear. And well, basically, this was the PV diagram of this very simple solid gas system. So if the volume is large enough, everything is gas, and it satisfies the ideal gas law. If you start compressing it, eventually solid phase forms. Once the solid phase forms, the pressure is independent of volume, and the pressure is constant for a given temperature. So that is why we have this horizontal line. And if you, once everything is solidified, if you try to keep compressing it, the pressure will increase very fast. Okay, any questions up to here? Okay, so let's look at the fluctuations now. What about the fluctuations in the number of particles? We said that the number is changing, and similarly the energy will be changing, because my system can exchange the number of particles and it can exchange energy with the environment. And for example, if we say that, okay, practically there are no fluctuations in these, in that case we could have just assumed that them to be constant. And so if we use the canonical ensemble or the microcanonical ensemble, basically we should get the same answer. So that's one of the motivations of studying these fluctuations. Now, let's remember, we have the grand canonical partition function, which is e to power minus beta e s minus alpha n, and r summed over all the numbers and all the microstates. And remember, beta turned out to be 1 over kt, and alpha turned out to be minus mu over kt. And then the number of particles, the average number of particles was basically summed over all states, Q, no, sorry, and R times the probabilities that the system will be have NR particles and will be in the microstate ES. Well, that is basically e to power minus beta ES minus alpha NR divided by the normalization. And in fact, we can write this as the derivative with respect to alpha of the logarithm of q. Of course, when we are taking the derivative with respect to alpha, I am keeping beta constant, or equivalent, you could just say t is constant, and I'm also keeping the volume constant. Basically, I'm changing alpha without changing ES. If I change volume, ES will change. Now let me look at the derivative of this n with respect to alpha. It's already the derivative of the logarithm of q with respect to alpha. Let me take its derivative once more. I will use this expression over there. You see, first the derivative of the numerator. Now that will just give me rs minus nr squared times PRS. PRS is the exponent divided by Q. Minus the numerator I'm taking the derivative of 1 over Q, so it becomes a minus Q squared times the derivative of Q itself, but the derivative of Q basically brings another factor of the numerator. So the first term is minus the average of n squared, the second term is n average squared. So basically this is the minus the fluctuation in the number of particles in my system. And again, I should remind you that I am taking this derivative at constant t and constant v. So the fluctuation that I'm looking for in the number of particles is given by minus the derivative of the number of particles with respect to alpha at constant temperature and volume. But remember, alpha is mu over kT. So if t is constant, the alpha is just d mu over kT. So derivative with respect to alpha at constant temperature is the same thing as derivative with respect to mu. So with a minus sign. So this is equal to kT times derivative of n with respect to mu at constant temperature and volume. Well, that derivative still doesn't look nice. I say nice in the sense that, okay, if you want to imagine a measurement that will allow you to determine that derivative, you have to be able to measure the chemical potential. Well, I don't know any device that measures the chemical potential directly. We have thermometers that measure the temperature. The number, well, we can measure the number of particles by a scale. We can measure the weight. If you know the composition, then we can determine the number. But chemical potential is not easy to measure. So I would rather express it in terms of derivative in terms of some other derivatives. Now let me remind you the differential of the Gibbs potential. So this was minus S dt plus V dP plus mu dN, and we know that G is equal to mu times N. We had already seen that. Well, if G is mu times N, dG would be N times d mu plus mu times dN. But dG at the same time, this is minus S dt plus V dP plus mu dN, which tells me that the differential of the chemical potential is a function of temperature and pressure. It depends only on, you see, G depends in general on on T, P, and N. So to show that G was actually equal to mu times N, what we did was G is an extensive quantity. So if we double the system, everything should be doubled. Well, the only extensive argument G has is N, so it has to be proportional to N. It cannot have any other independence. And the proportionality constant can be a function of the other two parameters, T and P. So mu in this differential is, I'm considering it as a function of T and P. So this is equal to minus S over N dt plus V over N dP. So basically, the differential of the chemical potential is minus, I will show it by small s.
So there is a minus sign in front of alpha, right?
Yes.
So shouldn't we be concerned about the convergence of the partition function?
Why?
Because the exponent gets positive, right?
What is the sign of mu?
Minus negative as well.
We didn't yet study mu. In fact, mu will turn out to be negative in general. So the mu is minus, this is small s is the entropy per particle. dt plus small v is the volume per particle, dP. Well, why did I want this? Well, you see, I have already shown that the fluctuation in the number of particles is equal to this derivative. So this basically tells me that I should change mu, keeping T and V constant, and look at how N changes. But if I keep T constant, the change in mu is actually equal to V times dP. So that derivative, which is the change in N divided by the change in mu, I can also write it as KT times dN over dP at T and V constant. Well, much better, but we can do even better than this. I would rather relate this to the volume, this derivative to volume, rather than the number of particles. I'm keeping V constant. So let me write N as V over small v. Remember, small v is the volume per particle. V is the total volume. If I just take the ratio, that gives me the number. So now, if I take the derivative with respect to P, pressure, keeping temperature and volume constant. Well, volume is constant, so I can just take it out. Now I need to take the derivative of 1 over the volume per particle, which will be minus 1 over V squared times derivative of V, P, T, and V, which will be minus N, just N, 1 over V minus 1 over V, del V by del P, T and V. Well, that quantity over here basically measures how much the volume per particle changes if I change the pressure. The fractional change in volume per particle as I change the pressure. So if, for example, this is large, Even a very small change in pressure would cause a large fractional change. If this is small, if this goes to 0, it will basically mean that even if I change the pressure significantly, the volume per particle will not change. So basically this measures the compressibility, how much you can compress your system. And in fact, it is defined as compressibility at constant temperature. How much you can compress it. In fact, V doesn't depend, the small v doesn't even depend on large v. You see, if you look at our arguments here, small v can depend on T and V, but it's an intensive quantity. If you double the system, it shouldn't double. It basically tells me that it cannot depend on V. So I don't even need to write the V dependence over here. It's just the derivative of volume per particle with respect to pressure at constant temperature. So that's why it's the compressibility at constant temperature, not constant temperature and volume. So what did we achieve now? We were looking at the compressibility, the fluctuations in the number of particles. This is my fluctuation. Let me also divide by n squared. I would like to find the relative fluctuation. Well, we had just seen that derivative is actually n times the compressibility. Well, let me simplify some factors. This is kT over V times kappa T. And if you take the thermodynamic limit, and V goes diverges, so this is 0. So relative fluctuations are negligible. Do you agree? Well, if I'm asking whether you agree or not, you should probably think that there's something wrong. What I'm saying is not correct in general. For most cases, this fluctuation will be negligible, but there is only one case. There is one circumstance under which it can be large. You see, I'm saying that I'm assuming that in the thermodynamic limit, V goes to infinity, fine, or it becomes very large. But I'm assuming that the compressibility is finite or small. But remember our last lecture when we had these phase transitions. You see, we had such a PV diagram. You see, at this point, V changes during that horizontal segment. V changes. So if you look at this derivative, some non-zero number, but change in P is 0. So compressibility diverges during a phase transition. You see, del V by del P, you can say that it is 1 over del P by del V. It's the inverse of the slope of this PV diagram. That slope is negative, and for solid, it's in fact huge. It's a huge negative number. For gas, well, it's a negative number. But in the horizontal segment, that slope is 0. So the inverse diverges. So that basically tells me that fluctuations in n are negligible away from phase transitions. But during phase transitions, fluctuations can be large. So as long as you are not close to a phase transition, fluctuations in number is negligible, so you can basically use canonical or the grand canonical ensemble. Because the main difference is the change in the number of particles. Well, they don't change much, so they should both give the same answer. But we had already seen that canonical and microcanonical, also the energy doesn't fluctuate much, so it doesn't matter which one you use, you should always get the same number in the thermodynamic limit. You see, the fluctuations are 0 in the thermodynamic limit. When n, v, they all goes to infinity. You see, these divergences, I don't think we will have too much time to study deeply these phase transitions, but what happens is, we will discuss it slightly today. During phase transitions, certain properties change discontinuously, like the volume per particle. In the, take water. If you compare the volume per particle of water and water vapor under normal conditions, well, there's a large difference. So there is a discontinuity, there is a non-analyticity over there. But you see, all of these properties, in principle, can be derived by the exponential from the sum over exponential functions. Well, exponential function is probably the most analytical function that you will see. Everything is analytical. Everything will be continuous. So the discontinuities, which are basically non-analytic behavior, only appears in the thermodynamic limit. When you take the limit, this analytical function, the limit can be a non-analytical function. So that is why we have divergences or discontinuities in phase transitions only in the thermodynamic limit. If we are not in the thermodynamic limit, everything will change continuously. Maybe very fast, but still continue. They will change continuously. Now, if we look at here, during a phase transition, I said that KT, the compressibility diverges, but typically, this compressibility diverges by some power of delta. So for a finite system, it will be finite, a huge number, but a finite number. But still, if you take the thermodynamic limit, on the one hand, we have the 1 over v, which changes as the number of particles. The compressibility kt, which scales as some power of n. And so these fluctuations might not be negligible. So if we are studying phase transition, the grand canonical ensemble is practically our only choice. Any questions here? Okay, so let's look at the fluctuations in energy. What about energy? Well, we know the energy of the system is given by E s e to power minus beta E s minus alpha n r divided by Q, which we can write as minus the derivative with respect to alpha of the logarithm of the grand canonical partition function. Well, if you take the second derivative of u with respect to alpha, yes, it's basically the same treatment as before. Before, we looked at the oh, sorry, this is not alpha, this is beta. When we were looking at the fluctuations in the number, we took the derivative with respect to alpha, which gave us the average number. Second derivative just gave me the fluctuation in the number. And similarly here, this will be minus the fluctuation in the energy. Of course, when I'm taking this derivative with respect to beta, I'm keeping alpha and V constant. Well, instead of alpha, you can say that I'm also keeping Z constant. Because remember, Z is e to power minus alpha. So if I want to study the fluctuations in energy, it's enough for me to calculate kT squared del U by del T at constant Z and V. Beta is 1 over kT, that's why I have d beta is minus dt over kT squared. So that's why I just converted it from a derivative with respect to beta to a derivative with respect to t. Well, du by dt is something we know. If, let's say, we were keeping V and N constant, this was nothing but the heat capacity of the system at constant volume. But here I'm taking the derivative of du by dt not at constant N, but at constant Z. So I need to first change my derivatives. So U, you see here, in this derivative, I'm treating U as a function of Z, V, and T. But I would like to have U as a function of N, V, and T. Of course, N itself is a function of Z, and V, and T. So when I'm taking du by dt at constant Z and V, I can just look at this expression of U. Well, there are T dependencies in two places. One, N itself depends on T, in principle also Z. Two, there's an explicit T dependence. So this will be du by dt. This is the derivative with respect to the explicit T dependence. Of course, when I'm taking this derivative, I'm keeping N and V constant. Plus, there is a dependence of U on T through N. I'm taking the derivative of U with respect to N, keeping V and T constant. Then I'm taking the derivative of N with respect to T, keeping Z and V constant. So if you like, this is the chain rule for this derivative. You see, you also see here that it's important to keep track of what you are keeping constant. Because in general, in mathematics, you just say that, okay, if you are taking the derivative with respect to one variable, all the other variables are constant. But here, well, you have the flexibility of choosing whatever arguments you like. So you have to specify explicitly which arguments you are considering. So in this derivative, I'm considering the arguments of U to be T, Z, and V, but here in this derivative, I'm considering the arguments of U to be T, N, and V. So those two derivatives are different. So that brings me to the fluctuation in energy. is kt squared times du by dt nnv plus kt squared du by dn vt times dn by dt, keeping z and v constant. And remember, this is CV. Now, if you check your notes, this whole first term, if you remember, we were looking, when we were discussing the canonical ensemble, we looked at the probability distribution. We had seen that it's the probability of energy is a distribution peaked at some average value, and the width of that peak was the uncertainty, which is the fluctuations in energy. It was exactly this expression over here. In the grand canonical ensemble is actually the energy fluctuation in the canonical ensemble plus some correction term. And we know that at least the relative fluctuation of energy in the canonical ensemble is negligible. Now let's get the second term. And I want to somehow, if possible, relate it to fluctuations in the number of particles. I want to find this, relate this second term to this delta n. Well, let's see. Let me check my notes. Okay, so let's first show this identity. Let me first simplify dn by dt. Okay. Now we know n. This was minus the derivative with respect to alpha of logarithm of q. We know u, which was minus the derivative with respect to beta of logarithm of q. Of course, when I'm taking the derivative with respect to alpha, I'm keeping beta and v constant. Here I'm keeping alpha and v constant, and keeping alpha constant is the same as keeping z constant. Remember our Maxwell's equations. So if we had two different quantities equal to the two different derivatives of the same quantity, if we take second derivatives, the second derivative should be equal. So the derivative of n with respect to beta at constant z and v is equal to derivative of u with respect to alpha at constant beta and v. Where will I use it? Well, I will basically change that derivative to a derivative of u. because the left-hand side over here is minus kt squared del n by del t at constant z and v. It is this term over here. Whereas the right-hand side is minus kt del u by del mu at constant t and v. Why? Since I'm keeping beta constant, t is constant, but alpha is minus mu over kt. So that's what I used over there. So if I do the simplifications, del n by del t is actually 1 over t del u by del mu. The nice thing is on the right-hand side, I don't have z anymore. Well, mu is somewhat equal to z, but at least I got rid of z. So back to here. Now del n by del t is actually 1 over t del u by del mu. Now I can relate it to the fluctuations in number of del n by del mu at constant tv is del n by del u at constant tv times del u by del mu. No, sorry. Yes. Well, here I only have del u by dn. I don't have del n by del u, but this is nothing but del u by del mu at constant tv divided by del u by del n at constant tv, or del u by del n. I'm just using the chain rule. At tv is equal to del u by del mu tv divided by del n by del mu. Oh, sorry, I will not use this. I'm basically rewriting delta n squared now. This is kt del u by del mu tv times del n by del u tv. And, well, okay, del u by del mu tv, which is the derivative appearing in the fluctuations in energy, is actually equal to the fluctuation in the number of particles divided by kt times del u by del n at constant temperature and volume. Now I put it over here. Instead of del u by del mu, this kt is cancelled. I have another del u by del n term, so I get the square of this one times delta n squared. Okay. So this is kind of the fluctuation in energy. Now, as I said before, there is this term, which is the fluctuation in the grand canonical ensemble, has a contribution due to the energy exchange, let's say, because my system is free to exchange energy, even if it doesn't even the number was constant, it can exchange energy with the environment. So that is the same as in the canonical ensemble. But there is also an change, fluctuation in the energy due to changes in the particles in my system. So just take the example of phase transitions. You see, if solid becomes gas, it absorbs heat from the environment, so you have to give energy. So the energy of the system changes whether more solid becomes vapor or when vapor becomes solid. It releases energy when vapor becomes solid. So those fluctuations in the number also cause fluctuations in the energy. This energy doesn't go anywhere else, but it basically goes to breaking the chemical bonds in my system. And, well, just like our previous arguments in the fluctuations in the number of particles, far away from phase transitions, you say this will be negligible. Because both in the relative fluctuation in energy in the canonical ensemble is negligible, plus energy fluctuations would be negligible. So far from, if you are not very close to phase transitions, practically there is no energy fluctuation, and hence in the thermodynamic limit, whether you use the microcanonical ensemble, or grand canonical ensemble, you should get exactly the same answer. The only difference arises in phase transitions, where you cannot just ignore that the numbers will be fluctuating rapidly between different phases. So in that case, you have to stick with the grand canonical ensemble. So sometimes students ask, which ensemble should we use? Well, if you are not looking at phase transitions, it doesn't matter. Whichever one you can use, just use it. But in the, if you are looking at phase transitions or another such critical phenomena, you have to go with the grand canonical ensemble. So basically, all this derivation, 50 minutes of derivation, the final result is away from phase transitions, there are no fluctuations. And close to phase transitions, you cannot ignore the fluctuations, and you have to use the grand canonical ensemble. Any questions? Okay, so let's give a 10-minute break, and then we will continue after the break.
Hocam, ben lab'a gideceğim, o yüzden biraz katılmayacağım.